So welcome to the third annual Pedro de Alba Lecture in Geotechnical Engineering. So I'm glad to see a lot of people here, and we're glad to have Professor Holtzen here. So we're pleased to see so many attend this event named after a colleague that was here for 33 years teaching the art of geotechnical engineering before losing his battle to ALS. So before I start the program, I'd like to acknowledge our sponsors, which really allow us to hold this event annually. And many of those sponsors have had Professor de Alba as a teacher and a mentor. So we're very grateful that our major sponsor is Halen Aldrich, so thank you very much. And also all the other generous sponsors, which include FDH, Hatchmott McDonald, Sanborn Head, GZA Environmental, Finley Engineering, Terracon, and of course the Department of Civil and Environmental Engineering. Special thanks also to Professor Gayomi for co-organizing this event, and also to Kristen. Where is she? She's in the hallway. Kristen? Yeah, so Kristen Peranto, she's really did a lot of work in organizing everything and coordinating travel and so forth. So thank you very much. You're the best. So in the event program that you have, you can see a little bit about Professor de Alba. I'll give you a little bit of background. He was born in Chihuahua, so I always gave him a little bit of a hard time because Chihuahuas, you know, this little tiny little dog that, but very popular with that food chain there. Yeah. Okay, this is not going anywhere. So Professor de Alba obtained his BS in '64 from the National University of Mexico, and then he worked as a design engineer for the public and private sector before obtaining his graduate degree at UC Berkeley. And he worked, while at UC Berkeley, he worked with Professor Seed on liquefaction of sands. He also worked after his PhD with Shannon and Wilson in Burlingame, California, so near San Francisco. So he got a lot of good experience in there. And then he joined civil engineering again at Berkeley and did so as a research engineer before he came here at New Hampshire, University of New Hampshire in 1977. So his work experience in this industry was really valuable, really a key asset to his teaching. I think a lot of his former students benefited from that. So he was able to merge practice with theory. So he was an outstanding teacher, as many of you know, a scholar, and above all, I think he was known as a gentleman. Very quiet person, but really a great person. He was a mentor and a role model to his students and colleagues. And he always showed a lot of great compassion to his students and to the University of New Hampshire. So as part of this evening program, we'd like to recognize one of our outstanding students with the Pedro de Alba Scholarship. This award is established in memory of Professor de Alba to benefit a student with an interest in geotechnical engineering and also a passion for the arts. So this year's recipient is Americo Santamaria. So. You can stay here. Rico got his BS from UNH, and he's getting ready to defend his thesis in a couple weeks. So he's a little busy, and I think he got a few gray hair. And I don't know what Rico's level of passion is for the arts, but he's got Italian heritage, so he's probably somewhat related to some famous sculptor like Michelangelo or something. But Rico is an outstanding student. It's really a pleasure to have him be the recipient. Congratulations. Thank you. So let's get to our speaker. So our speaker this evening is Professor Robert Bob Holtz. I don't know if anybody ever call you Robert, but maybe your mom or something when you were bad. So Professor D'Alba always talked very highly of you and truly enjoyed, like we all do, your book, An Introduction to Geotechnical Engineering. So initially it was published, the first edition was by Holtz and Kovacs, but now you managed to get rid of the other authors by having a third author. So it's Holtz, Kovacs, and Sheehan. So when you refer to your book now, it's Holtz et al. So I never could figure out who Al was, but so the other ones. So let me briefly highlight a few of your numerous accomplishments. So this barely scratches the surface. So you got a BS from an MS and a BS from University of Minnesota. So we got this nice weather for you. And also did a special program in soil mechanics from Harvard University in 1966, and one of the teachers was Professor Casagran, and got his PhD from Northwestern University in 1970. Started his academic career at Cal State University in Sacramento from 64 to 66. I didn't know that. And after his doctorate, he worked in industry and then settled in at Purdue University from 73 to 1988 before moving to University of Washington in Seattle until his retirement in 2008, sorry. So he's emeritus professor now. So through various sabbaticals and summers, Professor Holtz traveled all over the place and worked in places such as Italy with the Studio Geotecnico Italiano with Professor Yamakalski, in France at the École Nationale des Ponts et Chaussées, and at Terrasol also, who is a great engineering company with Schlosser, and in Canada, great country, outstanding hockey teams. And then in Sweden, at the Royal Institute of Technology and the Swedish Geotechnical Institute. So he's been a major consultant on numerous projects in the US and abroad throughout his illustrious career. His areas of expertise are many and include geosynthetics, foundations, reinforcing soils, soil improvement, soil properties, landslides, and investigation of failures. He received numerous awards, and more recently was the 46th Carl Terzaghi Lecturer. He's the author, co-author, and editor of more of 22 books, and so most of you know one, but he's got 21 others, and he would be happy to sign any of those after. And he has over 270 technical papers and major reports. So we're greatly honored to have Dr. Bob Holtz as our third D'Alba lecturer, and in a way, Professor Holtz and Professor D'Alba share this similar character traits. They're both very humble and brilliant. So, Bob.
Thank you very much, Sean, and good afternoon, everyone. Or I guess it's almost evening, isn't it? I'm really pleased to be here and to be able to honor the memory of Professor D'Alba in a very small way. He, as Jean mentioned, was a student of Professor Seed at Berkeley. And we used to call the University of California at Berkeley the California Geotechnical, or California Earthquake Engineering School. Because back in those days, that's basically where geotechnical earthquake engineering started. And Pedro and several of his fellow students in those days, they really started that field way before it became kind of standard part of geotechnical engineering practice and research. Today, I think you can say it really is part of our bag of tricks to be able to do geotechnical earthquake engineering, or at least somebody in your company is able to do that. Pedro was one of the pioneers in that. And as Jean mentioned, he was a real gentleman. Every time I met him, I it was such a pleasure to meet him, and those of you that know him a lot better than I do will agree. The subject that I have, as you see here, my title, it doesn't have a lot to do with earthquake engineering, but I'll mention it a couple times. When I first started going to Terzaghi lectures, and this was when I was still a graduate student a long time ago, the people in those days had either had a direct connection with Professor Terzaghi or had some, they may have been a student of a student or something, and they would always start their lecture by telling you this. Well, I couldn't do that, or I can't do that, because Terzaghi died shortly after I started my professional career. And, but the best I could do is when I was working in Sweden at the Swedish Geotechnical Institute, as Jean mentioned, these two photographs were across the hall from my office. And this was taken, the photographs were undated, so I had to guess when it is, but I had friends that had been present when he visited there. Shortly after the end of the Second World War, a little village about 45 or 50 kilometers north of Stockholm, which now is at the site of the present International Airport Arlanda. And the guy here in the beret is Professor Terzaghi. This guy, bald-headed guy here, is Walter Kjellman, who was the founding director of the SGI and inventor of the Kjellman paper drain. In the photograph on the right, there's Terzaghi looking at the installation. Here is a mandrel, a chain drive, and those of you that have been on PVD jobs or wick drain jobs, that should look awful familiar. Things haven't changed in 65 or 70 years from the way they were even back there. The other thing that's remarkable about these photographs is how they were dressed. Can you imagine showing up on site dressed like this? First, they wouldn't let you on because you don't have the eyeglasses and the hard hat and the steel-toed shoes and all that, but can you imagine? That's the way they did it in those days, and they didn't worry about it. So things have changed, and I think probably for the better. The two previous Terzaghi lectures were presented that had to do something with geosynthetics, or were Professor Bob Kerner at Drexel University in Philadelphia and Jean-Pierre Giroux, who is a consultant out of Florida. And even though I've had students that did projects on those subjects, and some I thought we did actually some pretty good work, I couldn't compete with these guys, and so I decided to work on soil reinforcing, which was somewhat different. It's interesting, let me take a minute to just talk about geosynthetics and civil engineering. If you work in any of these areas, you probably run across or are going to use geosynthetics and waste containment and pond liners and so on and so on. Geosynthetics have really changed the way we do those things. We can do them the old way, but you know, we can use a thick compacted clay liner instead of a geomembrane liner, but a lot of the regulations require you to use a geomembrane nowadays. In fact, Giroux in his Terzaghi lecture said that geosynthetics were the, and he emphasized that, most important development in civil engineering practice. He didn't talk about research. In civil engineering practice in the 20th century, and I've given this talk a lot of times, and I've always made that challenge. Can anyone come up with something that is more ubiquitous across so many areas of civil engineering than geosynthetics? And no one has challenged that. Certainly it's the first new material since the development of pre-stressed concrete, which was about 100 years ago by Freixenet, and there probably are other examples. So what I plan to do in the rest of the evening is to talk about reinforced soil from a historical perspective. And this is personal. It's not chronological. It's how I got involved in doing this. And I suppose being interested in history is a little bit a function of age, but I plead guilty. I'm very interested in history and the history of our field, as well as, in this case, reinforced soil. We'll talk about the advantages and basic behavior. I'll get into design and properties, and in those two areas, I'm going to emphasize some research that was done by some of my students at the University of Washington. It's a mature subject. Reinforced soil with geosynthetics is done almost routinely in a lot of cases, but there are a few things that we need to do and to fix. There are only two technical issues, and they would be a challenge, I guess, for students in the audience that here are great research projects. And then there are some serious professional issues that I think are very serious threats to our profession and this technology. I don't like to end on a negative note, and so rather than show you failures, I'm going to show you some examples so we can leave smiling, and then I'll have some final remarks. It's pretty easy when you start looking around. Reinforced soil's been around a long time. Birds and beavers have learned how to do it, and basically adobe bricks that are used at least in the southwest of the US, where I originally came from, are very common. After all, there were Indian tribes building 3-story houses and apartment buildings with adobe, where you take a soil or some material that has rather poor tensile resistance, and you mix it with something that has a good tensile resistance, and the composite behaves very, very well, like reinforced concrete. It's kind of the same analogy. The ancients in ancient Mesopotamia, modern-day Iraq, built these ziggurats, which were ancient temples. Some very impressive structures. This one was originally thought to be 87 meters high, now 45 meters. It's a ruins, but my God, it's 3,500 years old, so that's doing pretty well. And each one of those horizontal lines there is a woven reed mat or palm fronds or something, and there's an example of that. And when I gave this talk a few years ago, Jean-Pierre Giroux said, "Oh, I saw that ziggurat." He visited Iraq. He wasn't sure of the date. It was in the early 80s. And this is that ziggurat, the same one that I showed you. And here is the reinforcing layer. You go up here about 1 meter high, and there'll be another layer like that. And so it's performed quite well. And this is something that's biodegradable. You don't have to worry about maybe in a desert climate that deteriorating, because it's lasted 3,500 years, which is not too bad. Great Wall of China, especially the Western Wall. If that doesn't look like a reinforced soil slope, I don't know what it is. It's an amazing. I would love to go there and get a sample of that material and find out what it was. Well, I got into soil reinforcing and geosynthetics when I was working in Sweden in the early 70s. These two guys were very instrumental in my interest. Oleg Vager was the inventor of this. He was the idea guy. And Bengt Brahms was the director of the Swedish Geotechnical Institute at that time. And he was my boss, but he was a very willing collaborator. We did a lot of work together. He caught on what was happening, and he said, "This is something we should do," and developed design methods. Bengt was quite analytical, which I'm not, and so it was really fun working with him. And here's one of the early applications of reinforced earth or reinforced soil, I guess you could say, for reinforcing embankments on soft foundations. Sweden has a lot of very soft soils. They have a lot of problems with stability of even small embankments. And in the river valley out in the southwestern part of Sweden, Oleg built this test wall in 1966 out of sheet piles and tie rods. And in 1971, we worked at a job, and I'll show you some photographs of this later, of using geosynthetics instead of steel rods and channel sections, but the embankment then would be built over that, and this would reinforce it. It'll move and settle, but take up those horizontal stresses, and Oleg came up with this design method down here, and those of you that have studied slope stability, that looks like a classic moment equilibrium equation. And basically what we're doing with the geosynthetic is putting it in the base to replace the steel tie rods and whatever else you're using for the horizontal stresses. The first job was in the southwest of Sweden, not far from where that sheet pile section was, with a woven geosynthetic, and I'll just show you some photographs of it going in. It was very successful. It worked really well. I won't go into the details. I've got references but I think we understood how it worked, and it worked very, very well. And because of that, the weaving company gave us a small amount of money, it wasn't very much, to do some laboratory tests. Said, well, we'd like to come up with some way to design this stuff a little more rationally than just build it and see if it worked. So in this case, we had a pull-out box, and our idea was that that's what would happen at the edge of an embankment, that the geosynthetic would be pulled, or the reinforcing would be pulled and put into tension. And so maybe you can model that by using a pull-out test. And so I found a box down in the basement of the institute. So this was a low-budget operation, like most master's projects. You don't have a lot of money, and so you kind of do with what you have. And you can see the clamp here pulling the geosynthetic out of a bed of sand. We compacted the sand, got a lid on there, and there was a plastic airbag here, and you can see the hose coming up there for applying a normal stress. So we did sort of like a direct shear test, in the sense you pull this material out of a bed of sand. And we tried to have some instruments on there to try to measure strains, as you can see those magnets there. And I won't take a lot of time explaining this, but what we found is that stuff really stretches. In fact, we found that with a very low normal stress, the geosynthetic would tear. This was strong stuff. It was a woven polyester, multifilament woven. And it would tear before it would pull out all the way. And we found I'd use two different sands, that the slope, if I took normal stress versus kind of a shear stress here, sorry, normal stress, this is normal stress down here, shear stress up here, in the standard Moore diagram, then I have to calculate the normal stress in kind of a special way, which I think now, after all, this was 1973, we really didn't know what we were doing. The friction angle that we measured was very close to the friction angle triaxial test. And this was for a rounded sand with a friction angle around 35 degrees and an angular glacial sand that was about 43 degrees. So, wow, that gave us some idea that this is kind of how this stuff behaves. It doesn't pull out. You don't have to worry about it failing in that direction unless it's actually pulling out of the backfill. So then a year later did some work at the SGI, and actually at the Royal Institute of Technology. That's what KTH is, their abbreviation in Swedish. There's my daughter, who now, I've got granddaughters that are older than she was then, so I know exactly when this was, because I know how old she was. And there we had the geosynthetics with the magnets on there to try to measure strains. By then we'd found out about reinforced earth, and so we tried to model the wall. We said, well, maybe there's a better application with a backfill of a reinforced wall rather than embankments on soft ground, which is actually fairly local. And did some tests with a test pit. It was at the Royal Institute of Technology with a big X-frame here to put normal stress. They had these airbags. Actually, they were camping air mattresses. Put a normal stress on there, and we found these things would move. The walls were about 1.20 meters, so we're talking about 4 feet or a little more high. And boy, they'd move like heck. Well, you got a pretty flexible wood. Why wood? Well, that's what we could afford. So we found that these things will move a lot, even with very short reinforcing. They're going to move like heck, but the airbags would burst before the wall would fail. This material is really hard to fail. It's very difficult. And I've worked on several jobs where in research jobs, both in the field and in the lab, of trying to get a reinforced soil slope or a wall to fail. And you've got to work at it really hard to get it to fail. This stuff is incredible in how it works. Well, as I mentioned, reinforced earth had started. The terra armée was invented in the mid-60s, actually. The earliest publication I found, that was invented by this guy, Henri Vidal, who was an architect. He wasn't even a civil engineer. And this La Terre Armée, 1966 was this publication, the oldest publication I could find. And here you see he's got a skin on the face. This was metal, sheet metal, as you can see, and metal strips going into the backfill. That's basically what reinforced earth is. And I found this photograph in that publication. I'd forgotten it the original, and we'll talk about that in a minute, but you'll see that again later. It's interesting that he spent a lot of time telling you why you needed to use a metal skin, and that's why this is here. So they built some high retaining walls on a freeway in the south of France that saved an enormous amount of money. And so this really revolutionized how wall construction or steep slope construction was done, both in France and in the rest of the world. It came, within a very short time, Vidal started with the reinforced concrete panels, that kind of cruciform panel that he patented, and that I think that's the standard wall that Reinforced Earth Company or Terra May uses throughout the world. I first visited France in 1976, and Terra May was kind enough to take me out to the west of France after one of these wonderful French lunches with lots of wine and cheese and everything. So I was really softened when we went out there. I tell you, it was really a lot of fun. And here you see, here's the panel. They precast these tabs in there. Here are the strips coming in, nutted and bolted to the panel, and here's the backfill. So they'll bring another layer of backfill in, and you can see the construction. And you can get some very impressive structures. They're very flexible. You don't have to spend a lot of money on the foundations. And so it's pretty impressive structures. And this technology has been used all over the world. There probably are 50 or maybe even 100,000 reinforced earth walls around the world today. Well, the first one that was built in the US and in fact in North America, was in Southern California, the Angeles National Forest. There was a state highway that went through the forest, and it failed. Here's the landslip that had occurred, a landslide, and some photographs of the wall under construction. And you can see from the people standing here and the equipment that it's a pretty high wall. And then you look at the section of the entire failure. That's this little wall up here. So this was a big landslide when you think about it, how that much occurred. And this led to some research that was done at UCLA with the late Professor Ken Lee, who died tragically at a fairly young age. And Lee, his first experiments, of course, he followed what Terra May had done with the metal, made some model tests with metal facing system. And what he did was allow this to fail. He had these struts here, and he had instruments and strain gauges on the steel or the aluminum strips. And here you see this black line is where the wall originally was, and it moved out about 50 millimeters, and you can see some failure lines through these bands of colored sand. And if you put a protractor up there, you'll find that the failure line is very close to, what would you think, those of you that have studied backfills behind retaining structures? Yeah, 45 plus phi upon 2. That was just amazing. And that observation plus the fact that Lee and a couple of other of the pioneers were geotechnical engineers, and the way they teach earth pressure theory changed our design practice for the last 30 years. Now, you say, well, this isn't fair. It's failed, but it's supported. What happens if you don't support it? Well, it falls down, and that will happen in the field. This is not something that's in civil engineering we like. In fact, that violates the health and safety, our canon number 1 in our code of ethics, that health and safety must be protected above everything else. Collapse like that, we really don't like at all, that kind of failure. And so that's potentially something that we need to design for. Now, this doesn't happen very often. As I said, this is hard to get these structures to fail, whether they're steel reinforcing or geosynthetics. And it's interesting that when you start looking at the early history, I found this paper by 2 Frenchmen using a geosynthetic. And they built a wall that's about 2 meters high, wrap face wall, reinforced with a non-woven polyester in the early 70s, and nothing else was done after that in France. And the only thing I can see is Terra May dominated, reinforced earth dominated. They had the market and the other, whatever they needed elsewhere to dominate, and no further experiments were done with polyester or any kind of geosynthetic. But that wasn't true in the US. In the Pacific Northwest, these guys with the Forest Service built some walls that look an awful lot like those ones in France. This was in the early 70s, about a 2-meter high wall that was built in southern Oregon in a national forest. And Dick Bell was a professor at, he's now an emeritus at Oregon State University. He advised them on how to do things and how to design. And they had a publication. This is actually from the Federal Highway, but the original was published by the Forest Service the year before, and all Federal Highway did was tear the cover off and put their own cover on there as one of their technical memoranda. But it's basically the same stuff. And they built some quite impressive structures. None of them were really very high, 20 feet, about 6 meters. They had to use shotcrete on the face because that protects against ultraviolet radiation and also against vandals, which apparently they had trouble with in southern Oregon. I don't know what kind of weird folks are running around cutting the wall faces, but anyway, 3 inches of shotcrete is a very effective deterrent. This led to some research at Oregon State, sponsored by Federal Highway, on test methods. At this time, the test methods we had for geosynthetics or for synthetics came from the fabrics industry. So carpets, drapes, I don't see any drapes here, suit clothing, pajamas, were all tested according to ASTM standards. And this work was done it was published in 1980, was the interim report, started about 1976 at Oregon State. I was on some kind of a review panel for this, so I got this copy. And I also got a draft copy, as you can see, for the final report. It was never published by FHWA. And I thought, that's kind of weird. So I was out at Oregon State and met Professor Bell, and I said, what's going on? How come that was never published? And he said, well, they wanted me to change something, and I didn't want to change it. And so that led to these 2 stubborn guys that just refused to compromise. And Federal Highway said, okay, fine, we'll never publish it, which I think was really a shame. This led to, they realized they needed to educate highway engineers. So the Federal Highway contracted with Professor Alba Halliburton, who at Oklahoma State, the other OSU, Oklahoma State, and he died young too. And then Barry Christopher and I took over the contract, and I said 150 courses here. It's probably 175 or 180 now. And I'll brag a little. I think it has really helped highway engineers. Certainly it's improved their specifications and helped them with their design and highway practice. This is the cover of the first geotextile engineering manual. It was published originally in 1983. And then I think the Federal Highway put a number on it finally in '86. There's Barry and myself, and that's our cover, and it was a monster. I mean, look at the number of pages. What were these guys thinking? 2 reams of paper thick. We had everything in there. But actually, it's not bad. It's even this old. I'd say that. So that gives you a little historical perspective, I hope. Let's talk about some advantages in basic behavior. An important engineering attribute or characteristic is cost. What are we talking about? Well, it turns out, I don't care how you measure these structures, but usually it's dollars per square foot of face or per square meter versus the height of the structure. And once you get more than about 10 to 12 meters, there's almost no competition. Structural walls go up a lot. So reinforced concrete cantilever walls or those kinds of walls go up almost exponentially. And you find reinforced walls are kind of going down in this area here. I'm going to show you some photographs of the Rainier Avenue wall that was built in Seattle a few years ago without a permanent face, but we probably could have spent a lot of money on a very nice architectural treatment and still been cheaper. And that was about a 12-meter high wall. They're very flexible, very tolerant of settlements. That means you can save some money on the foundations. Easy to change the alignment and grade. Very important that they're seismically stable. They absorb a lot of energy. You may crack the face and that sort of thing, but they're not going to fall down under a earthquake event. I don't know if you guys worry about earthquakes in this part of the world. We sure do in the West Coast. And that's an important attribute. Simple, rapid construction, something I never thought about originally, but you can have the facings green, have them grow things, and I'll show you some photographs of those later. And that makes them very attractive and very, very environmentally friendly. You can make steeper slopes reinforced with geosynthetics, a lot steeper than these slopes would normally stand whether they're granular or cohesive. And in fact, they're safer if they're reinforced. Jonathan Cheng and Barry Christopher, a number of years ago now, for the same calculated factor of safety, they showed that you have a lower probability of failure, and that means a more reliable structure if it's even a reinforced steeper slope than an unreinforced flatter slope. So I asked the question, why do we even design and construct unreinforced slopes? Even at the same angle, put geosynthetics in there and they're going to be a lot safer. So, and a lot more reliable. So anyway, they've got a lot of advantages. I showed you this from the Vidal photograph. Barry Christopher gave me this slide a few years ago. And you can see he didn't Vidal made his vertical. Barry was afraid to do that, so he sloped his back a bit. But look at that. You say, gee, what forces are acting at the face? If we're going to build a regular retaining wall, we talk about earth pressure theory, we have a lot of force against that applied by the soil. But if you do this, there isn't very much force there at the face. You don't have to retain much. So you say, well, that's not very, the particles are the same height as the spacing between the layers of reinforcing. That's true. And in fact, if I use smaller particles, I could have either more layers in there reinforcing, which is one way to do it, or I could have a very thin, modest facing just to retain the material in between the layers. And that's all you really need to do. And excuse me, you see this out in the real world. The steep slope and this part of a wall here, and I won't go into why that's the case, but you can see the layers are reinforcing, it's wrap face, and you say, well, gee, how can it stand there? Well, there's enough cohesion, enough fines in there, enough moisture in there that you get some negative pore water pressure, and it's able to stand on a vertical slope. In fact, you can calculate that very well. You know the stability number is about 0.25 or 0.26. You can calculate what the undrained shear strength is to maintain the slope vertical for that height. And it happens in the real world if you want. This was a guy, Bob Barrett, this fellow standing here. I asked him one time, what did you use for reinforcing? He said, oh, I went down to Walmart and got some cotton bed sheets, the cheapest ones they had. And that's what he built this wall, I guess you could call it. You can see the angle of repose here. It's about 30, 35 degrees. And in fact, what he did is he cut the face after he'd built this up, he cut the face there. And you can see it stands safely on a vertical slope. He's been criticized for this because he's not wearing a hard hat. But like one of our other friends pointed out, I said, that's okay, Bob's a geologist, so that's okay. And besides, he's leaning, so it'll fall over the other way. But this stuff's really remarkable when you think about it. And so the conclusions are that the stress at the face of a wall or a very steep slope are really rather small. It's only necessary, that face is only local to retain the soil right between the layers of reinforcing. It's not necessarily have anything very heavy or chunky or strong. Now, the Japanese have had different experience with their walls. And that I won't go into all that, how they build them, but they build them hell for stout. I got to tell you that, the way they put the faces of their retaining structures, and they claim that they get better performance. And I can't doubt full field empirical evidence, because they certainly have a lot of experience with earthquakes in Japan. But I'm not sure if we had the side-by-side where they got exactly the same shaking, that some kind of a wrap face light reinforcing wouldn't perform just as well. I don't know that. And some other material that's been used a few years ago, this was developed in France, called Texol, which is kilometers of a very fine filament that's sprayed and woven throughout the sand. And you can see, again, the angle of repose here. And you can stand this stuff on a very steep slope. So remarkable, with a very dry, as you can see, cohesionless material. So remarkable material. Let's talk a bit about design. You design a wall, and I'm going to put that in quotes because I think instead of calling these walls, we should call them very steep reinforced soil slopes. External stability is conventional. You make sure that you've got adequate bearing capacity. Overturning probably won't overturn because they're very flexible, but at least keep the resultant through the middle third. Make sure they don't slide, and don't forget the overall slope stability. Internal stability, there are several approaches, and I'll talk about that. Drainage. I'll say that 2 or 3 times. Very, very important in these structures, and just as it is behind conventional retaining walls. Seismic design, if it's appropriate for you, and then we'll talk about material properties in the next section. External stability, these structures will fail. Both of these happen to be reinforced earth or terra may walls. Clearly a bearing capacity failure here. The external stability was inadequate. Same thing here. They probably lost toe support because of a slide that occurred down well below the toe of the slide. Notice they didn't collapse like that one I showed you in Tennessee. These have undergone enormous deformations, both laterally and vertically, but they didn't collapse. That should give you a lot of, if you're a designer, a lot of confidence that somebody standing down here, they may go for a ride, but they aren't going to get killed, which is really, really good. So, internal stability. Let's talk about design. These walls were a combination of conventional earth pressure theory, Rankine typically, and terra may. And terra may said the same failure modes are that the strips would pull out, they'd fail in tension, and then you had to worry about creep, which probably is this interaction between the material and the soil. Now, this was a design approach that was developed by Ken Lee. You saw his failure surface, 45 plus phi upon 2, and being a classically trained geotechnical engineer, we teach retaining structures, say, yep, that's earth pressure theory. So let's do an earth pressure theory, earth pressure analysis, and have tieback forces or something that comes back from that. And Dick Bell at Oregon State with the Forest Service did that same thing. That led to what is called the tieback wedge approach. It turns out it's very conservative, as I'll show you. For reinforced slopes, it was the same idea. You did a classical slope stability analysis, and then you got these strips of geosynthetics going into the back. So what's the difference between a geosynthetic reinforced slope and a very steep geosynthetic reinforced slope? When does a very steep slope become a wall? And I wonder if the soil knows the difference. So Professor Bob Kerner, I was talking to him about this one time, he said, these design approaches depend on the way we teach. It comes back to the faculty, professors. We teach geotechnical designs for slopes and retaining walls separately. It has nothing to do with reality. And I said, well, boy, that's really kind of condemning, I've been teaching retaining walls, I teach class on slope stability, and gee, you mean I'm guilty of this? So I thought, well, I'll look and see what the experts say. So I looked in this book, it was put together a few years ago, And here they got Chapter 8, reinforced soil slopes. And Chapter 9, reinforced soil, geosynthetic reinforced walls. And I thought, well, they're a bunch of amateurs. What do they know? I'll go to the Bible. Professor Bob Kerner, Designing with Geosynthetics. I think he's up to the 6th edition now. And same thing. He's got it organized a little differently, but you got a section on reinforced slopes, and then you come a few pages later, there's a section on reinforced walls. Thinking, well, gee, something's wrong. Not sure what's going on here. Well, there are a number of current design methods that have been used, and basically, if you're going to use the tieback wedge or any of these methods, you're going to make some kind of assumption for the earth pressure distribution. If you do tiebacks or strutted excavations, these should look familiar, and that's basically what it is. And some of them are for reinforced earth, too. We don't worry about that. And basically what's happened is we've strain gauged RECO walls, or reinforced earth walls, and measured the horizontal stress. So you have a tributary area and the stress that's applied here, and you measure the strains, you know the modulus of steel, you can get the stress, so you know how much horizontal stress is applied to that wall, and compared that with the overburden stress at that elevation. And then this is related, this is in AASHTO, they relate this, the coefficient of active earth pressure is calculated from a knowledge of the friction angle, you know, 1 minus sine over 1 plus sine. Problem is the measured K is often less than Ka, the measured KH. And you think, that doesn't make sense. And you think about what they taught you in earth pressure theory. We started with the Mohr circle. Here's the vertical stress, the horizontal stress at rest, and then the wall moves away from that imaginary plane in this bed of sand. Everybody goes through this. I used to teach this. You all remember that. And you get to a place where, bingo, it fails. And why is that? Well, because that combination of vertical and horizontal stress, the active earth pressure, reaches the Mohr failure envelope and fails. It can't be less than that. And you wonder, how can you measure something down here when it's already failed? It just doesn't make sense. So I thought about this a little, and there are several reasons that is what's happened during the field measurements. The Mohr failure envelope is curved. Now we draw it, you know, if you look in these textbooks like ours, there's a nice straight line through the origin. Well, that isn't the way the soils really are. That's why you do the tests. But really, when you get down close to the origin, the Mohr failure envelope is curved, and so the phi is, there's no intercepts, there's no cohesion, if you will, but no intercept. So at low confining pressure, you got a very high friction angle. Also, if you're measuring triax or direct shear, the friction angle in plane strain is much higher. I've never seen a round wall. They're all plane strain. And the friction angle in plane strain is 1.5, 1.65 is much higher than the triaxial friction angle. At field densities, you get a high friction angle. You almost can't put sand behind a backfill in a retaining wall. With any kind of compaction, you get pretty high field densities, pretty high relative densities. Ranking theory is violated by anything that's in that backfill. That's a homogeneous isotropic backfill in ranking theory. So if we've got sheets or strips or bar mats or something, why are we using ranking theory? Apparent cohesion, probably, I've shown you several examples of that, probably in those measurements, the field measurements, there was some cohesion there, which they didn't measure. We didn't go and cut that slope vertically and just see what would happen. But had we done that, we might have found some cohesion. A little C goes a long way. If you've ever done stability analyses, you say, gee, you know, I got the lab tests that came, what, 150 PSF, and boy, I'm just a little bit short on that factor of safety. Well, gosh, I could kind of change that slope. What if I use 200 PSF? That's nothing, nothing. Bingo, you've got your 1.52 and everybody's happy. You can go away. A little C goes a long way. It's just amazing. And then field measurements. I don't know about you, but I've done a lot of field measurements. And there's always something that's wrong. There are always anomalous readings, things that don't work right, gauges that don't work at critical days and loading. There just always seem to be problems. I don't know if we're just not very good at instrumentation or these were low-budget jobs or something, but never worked very well. So I don't have a lot of confidence in field measurements. Now let's talk about reinforced soil slopes. I mentioned they were a combination of classical earth pressure theory and tieback forces. How do granular slopes actually fail, and how do we do stability analyses? So let's start with the sand at the angle of repose, and you see an example there of 30 degrees of rounded Ottawa sand. And if I had a slope that was 26 degrees, how much reinforcing is needed? Well, not very much. It's very safe. If I had a sand that was 35 degrees and I wanted to build at 38 degrees, how much reinforcing is needed? Well, not very much. Whatever I need is just to kind of restrain that little wedge. And what happens if it fails? I've got a maintenance problem. This little wedge is going to slip down at the angle of the repose and everything's fine. Well, so it wouldn't take a lot of reinforcing to maintain stability. There are design approaches that have been developed over the years. I won't take time to go into all those. But basically, it's like any stability analysis. You assume some kind of a geometric surface that you're able to analyze. Does the soil know it's supposed to behave that way? Doesn't matter for design, does it? You can assume anything you want. Not quite, but you know what I mean. There are a lot of reinforcing soil programs out there. I found 10, and I'm sure there are others that have been used. As far as I know, they're all okay. Some people have done studies to analyze, well, this method's slightly better than that. As far as I know, they're probably okay. However, if you're going to use any of those, read Duncan and Wright's Chapter 8 in their book on shear strength and slope stability. That is just on reinforcing. Has some very good words of wisdom in there for you. So let me talk about our research on geosynthetic reinforced walls. These are the two students that I had, Wei Feng Li and Fuzzy Saidin. And Wei analyzed reinforced walls, developed a working stress analysis, calibrated his model, he used FLAC, calibrated this with the Rainier Avenue wall. Now I'm going to show you that in a minute. We had field data there. Did plane strain tests, and at low confining pressure, and therefore was able to get the correct dilation angle. If you want to get good measurements with FLAC, you've got to have the correct dilation angle. It really is enormously, it just changes everything. And he made true Class A predictions of 3 walls that were built at Royal Military College in Kingston, Ontario, and got quite good agreement. Both external and internal performance can be reproduced if you have the correct material properties. And you think about it, surprise, if you have the correct material properties, you should be able to get the right answer. And if you have the correct boundary conditions, or at least are correctly simulated. And here's some data, and it isn't perfect. Here's the deflection, and at the same time measured the strains in the reinforcing. And I felt like that was pretty good for Class A predictions, and the differences in the wall face movements were about 5 millimeters, and this was on a 10-meter high wall. You can't see 5 millimeters in a 10-meter high wall. It's really quite remarkable. Fuzzy Saidin did the back analysis of a wall that was built in Louisiana of poor draining material on soft soil. It was 6 meters high, built by the Louisiana Transportation Research Center. And she used FLAC also, did her own lab tests, and considered effective settlement, infiltration, compaction. And she used FLAC, and one of the nice things about FLAC, you get a lot of pretty pictures. This is true for what's that other one? What's the other big that's popular? Yeah, Plaxis. You get pretty pictures, and she'd come in there, and I said, boy, that's got to be real. I mean, look at that. Isn't that fantastic? You have to believe it. But actually, she got pretty good results of what was happening in there in the ground. So her design recommendations, I think, are very useful for us. You're okay to use geosynthetic reinforced walls for soft foundations. Virtually every analysis method that's been developed is on a rigid foundation. The tests are on concrete walls, or we assume that the foundation doesn't move. The reinforced layer will give you more uniform settlement. No surprise there. Traditional settlement analyses are okay, so you can design these structures as you do any settlement or any foundation design. Shallow foundation, and then the settlement analysis, independent measurements. Rate of construction is important, and she did some infiltration analyses, and adequate provisions for drainage are critical. Drainage, drainage, drainage. And is this something new? No. These sketches came from Terzaghi Theoretical Soil Mechanics, 1943. I'm probably the only person in this room that was born before that was written. So this is standard geotechnical practice. All this, you know, he's got this for different, there's the earth pressure, or the pore pressures at different elevations, telling you where to put the drainage if you have infiltration or water moving in from a back slope. This is standard practice. There's no excuse for not doing this the right way. We know how to do this. And in fact, Dean Sandre, who's a wall guy in Southern California, has come up with a design like this to take care of drainage. He has a low permeability backfill, he's got back drainage, he's got all sorts of stuff in there, and you look at that and you say, wow, that's expensive. Yep, but so is a failure. A failure is expensive too. If you're going to use anything in here that isn't free draining, you better pay serious attention to drainage. Excuse me. There are a couple of other approaches. We did a little bit of work following on some work that was done at Davis in the 1970s, a composite material approach. That was what was published here with Wei Li and myself and a couple of my colleagues. And the K-stiffness method was developed by these two guys, Tony Allen of WSDOT and Richard Bathurst of Royal Military College of Canada. This is empirical, purely empirical, based on case histories. It's independent of reinforcing material. Why should there be a different, AASHTO has a different method for steel and one for geosynthetics? Why? Does the soil know the difference? No. More accurate estimate of reinforcing loads, and there's a step-by-step procedure that's consistent with LRFD that we're supposed to be using nowadays. So, if you want to design geosynthetic reinforced soils, and you want to use traditional limiting equilibrium methods, you're very welcome, but use the correct soil properties. Now, it's easy to say, it's not easy to do. There are very few plane strain devices available. It's hard to conduct triaxial and plane strain tests at low confining pressures. I've tried it. It's too many failures. It's been estimated there's something like 1 or 1.5% of these structures have had problems. That is a horrible record. And it's due to, it seems to be poor quality backfill, poor drainage, construction problems, the grid's going in the wrong direction, inadequate global or overall stability, and I showed you external stability, and I showed you some examples of that, unexpected surcharges, et cetera, et cetera. There is a disconnect between the wall designer, the geotech record, and the site civil. And I can tell you again, many, many stories of that. That is silly. These folks working for different people, and they don't talk to each other. And mistakes are made on sites that lead to problems with these structures. And it's complicated by wall designs that are supplied by materials suppliers and distributors. This is really a bad situation. Now, my friends and myself, we make a lot of money getting involved with attorneys on investigating these things, but it doesn't have to be. There are other problems. Lack of proper inspection. What? You mean you're putting up a huge structure and you don't have an inspector? Well, he's over there doing something, or we got a freeze on hiring, or we don't have money for it. No control of the construction by the designer. Economic pressures. If we can't get some engineers, if those engineers won't approve on-site materials, we'll get some who will. That was a job that failed in Prescott, Arizona recently, probably 10 years ago now. 60-some-odd foot high structure. Big box company, I won't say who, but that was their project manager. If we can't get those engineers to approve on-site soil, we'll get some who will. That's terrible. And I hope I don't, there are economic pressures to do that, obviously. And I hope I don't insult anyone, but I hate value engineering when it comes to this stuff. Now, I know it's all the rage and everything, and it may be good for foundations and other things, but it's terrible in this situation. Contractor supplied designs. Oh, have we got a deal for you, Mr. Owner? We can save you a lot of money. You know those geotechs are always over-conservative anyway. Everything's over-designed. And so then they come back to you and say, well, we want to do this. It's going to save some money. And then, so what happens? You say, well, gee, could I have some hours to check this? Oh, no, sorry, we've shot the budget for design, so too bad. What? We don't train workers. I've been on construction a lot, and I think workers would like to do a good job, but they don't know any better. So we need to take time to train the workers how you want the grids put in, what direction, some things like that. It's real simple to do, but somebody has to do it. And I've heard this in Seattle. I don't know if it's true here. Do you avoid liability by having somebody else do your design, vendor-supplied designs? I've heard that. Oh, we can't afford the liability. What happens if there's a problem? Yeah, they go right back to you, right? They aren't going to the guy that sold you the wall. He's a P.O. box in Atlanta or something, you know. What are they going to do? That's crazy. And if not, why do you give away good billable hours? I do not understand that. If you don't shift the liability to someone else, why do you give away those hours? And I can tell you fixing problems is a lot more expensive than doing it right in the first place. Proper design and inspection controlled by the designer will save a lot of problems. I've heard numbers like a factor of 9 in 10 to fix structures that fail. And certainly if you calculate all the legal costs that go into repairs of failures and whatever else is involved, it's terrible. So anyway, that's I think a real problem. And I hope this is not true in the Northeast. But I can tell you in our area, there are jurisdictions, namely the city of Seattle and some of its suburbs, that say, aha, that's a wall. It's got to be stamped by a licensed structural engineer in the state of Washington. What do you mean? Structural engineers, you know, they're great people. They know a lot about reinforced concrete and steel. They don't know very much, in fact, probably nothing about geosynthetics and soil reinforcing. And whatever they had in their undergraduate soil mechanics and hydraulics know a little bit about drainage and soils. And then besides, they're not responsible for the inspection. What? And yet, I could tell you stories of failures there. And I thought that was just our problem. And I gave some lectures in Australia recently. Well, it was a couple of years ago now. And a guy came up to me afterwards. They had their little happy hour afterwards and not before. And he said, oh, well, I was waiting for you to get started. I found this brochure. And I'm sorry I didn't bring it in. I was thinking about that this morning. I should have brought it to you. It was from the Institute. The talk was in Sydney at the Institution of Engineers of Australia. Ooh, boy, that sounds pretty good. And there was a brochure there that said, need a retaining wall? Hire a structural engineer. They got the same problem in Australia that we do. You have a retaining wall? Hire a structural engineer. So I don't know how to fix this. This is leading to all those failures I mentioned earlier. They're costly, potentially tragic. I gave this talk up in Ontario, and Richard Bathurst said, oh yeah, there was a wall that failed in Panama and killed some children. And the designer and supplier came in with big rolls of Franklin's and bought off the family. Can you imagine what would happen to this technology if that had happened here? Hits the papers, kids killed in South Carolina from a collapse of a reinforced wall. That would kill this technology. Now, there are some, I don't know who is responsible for that. I don't know how to fix it. Is it the Geoinstitute, the ASFE, or whatever it's called now, Geotechnical Engineering Association, or whatever it's called, Business Association, International Geosynthetic Society, ISSMGE. Is it up to us as individuals? They're not, a lot of these issues about hours for the designer and proper inspection is not unique to geosynthetic reinforced soil, but it threatens this technology. It's a wonderful technology, and I think it's a threat to our profession. And I wished I had an answer for you on that. But like I said, I want to end on a sour note, so I want to end on successful. And this is in Colorado, a bridge abutment on shallow foundations crossing an interstate highway, I-25, near Denver. And is very heavily instrumented as geogrid reinforced modular block face wall. Performed beautifully. Enormous amount of money saved on piles that they had to pre-bore through those stiff clays to get the piles in. But that was their standard practice. All bridges have to be on piles. In Colorado, Bob Barrett, that guy I showed you earlier, has done a lot of work with different faces, timber, modular block, or cement blocks as he calls them, natural rock, colored cement in the concrete. I think some wonderful things. And then you find some walls, probably a lot of these are steel reinforcing, but you find some wonderful things to make them less ugly. Walls are ugly. And so if you can make them less ugly, that's pretty good. The modular blocks that have been developed, these precast concrete blocks, and you can go around corners and you can do a lot of stuff that really are quite attractive. And green facings, I told you about this. This is with a steel wall, but it developed that. It was totally unplanned in a wet climate. Same thing in Taiwan. You can see the grids are still stacked here. They haven't even finished construction. And already in a subtropical climate, natural vegetation is established. And I'm sure it was for a housing development. You go up here and up, they were going to build houses up here. I'm sure in a few years you won't know that that was a reinforced soil wall slope. All these people driving up there to live in their houses, they never know that they were working on reinforced soil. And here you can see the facing system. I had a chance to go down to Colombia a few years ago, and compliments of Geosistemas Pavco, which is a manufacturer, and they took me out and showed me some of these structures. This is the way they do rural highways with sandbags, bring backfill in and the geosynthetics and then build them up very, very fast. And it works beautifully. They've done some really nice jobs. These two photographs I took in Medellin, up in quite a ritzy part of the city, gated community and all this sort of thing, and some really expensive homes. And that's all reinforced slopes. And then I got these photographs from this guy, Fernando Cano of Medellin, and he said, you can use these to show your friends in North America, but please tell everyone that not everyone in Colombia, please tell your friends in North America, he said, that not everyone in Colombia is a drug trafficker or a guerrilla. And I'm happy to say that these engineers in Colombia, and I've talked to landfill folks as well as reinforced, they are very innovative. They've done things that I think put us to shame. And we think we're, the best in the world and all that sort of thing. But I got to say, the folks in Colombia are fantastic geotechnical engineers. And some slopes, Northern California and Northern Idaho, reinforced soil. And then I almost took this out this morning because this has failed. And nobody knows why yet. We were talking about this before. They hadn't quite finished when this photograph was taken. It was taken out of an airplane window. You can see a drop of rain. The guy that took it gave it to me. They still had 20 or 30 feet. You can see the construction equipment here. This is a big slope, 250, 260 feet, something like that. And it failed just recently. You can go in and look at Yeager Airport, Charleston, West Virginia, and there's some wonderful photographs. There's some TV footage. It is spectacular. I'd love to be able to tell you what happened, but that has happened. Earthquakes, very forgiving. This is the Japanese National Railway in Kobe. Kobe was devastated, as you can see here, 1995 and 92. It's not exactly the same place, but the same stretch of the wall. that it settled and moved, and you know it went for a ride looking at that damage. And the JNR was still operating the next. Not easy to do. And if you're going to do modeling with FLAC and some of these modern numerical methods, make sure you have the correct dilation angle if you want to get the correct answer. For internal stability of steep slopes, I think design it as a very steep slope and then see what forces you need to maintain stability. As the slope angle increases, as I've shown you, more and more stronger reinforcing is going to be required. And after I looked at this, I found this paper. I had to clean out my office when I retired. And I found this report from Virginia Tech by Mike Duncan and one of his students on reinforced slopes, analysis of reinforced slopes. If you can get a copy of that, that's very useful, and you're doing design of reinforced soil slopes. I think you should use thin layers of weaker reinforcing. Not only is it cheaper, but you'll get better face control and better compaction. Pull out, it's not a problem. Based on the research that I showed you earlier in Sweden, the geosynthetic ruptures before it pulls out, but I've heard John Paulson's one of my friends in Atlanta that does these walls, and he said, yeah, but there's always some joker that stacks soil right near the face and it pulls out and everything fails. And he said, well, he didn't design it that way. I said, okay, so what does he do? He takes the top 2 or 3 layers and runs it way back in the backfill as far as he can. Cheap insurance. Cheap insurance, and it protects against unknown loads at the face, or at the surface, near the face. And don't forget, drainage, drainage, drainage. And also, if you're going to use traditional reinforcing methods, it's easy to check the statements, the K stiffness method, and let us know how it works, because we don't have very many case histories of it, so I'd like to know. So let's talk about soil properties. Basically, there are 3 components I've already shown you: soils, geosynthetics, and the facing system. Soil properties, as usual, clean granular backfill. We wouldn't design a reinforced concrete cantilever wall and use on-site poor draining backfill. Heck no, we'd spend the money for some good free draining backfill. Federal Highway and RICO have some very good specifications on that, limiting the amount of fines and the PI. I think those are very good specifications. And don't forget about the foundation and slope. Don't forget about drainage. I'm showing you this again because it's very, very important. And it is a design and construction issue. You may specify the best material. How is that actually going to be installed behind your structure or in the backfill? Somebody has to be out there watching and make sure that it's done properly. Geosynthetic properties, tensile strength, soil geosynthetic friction, that's that pullout. I don't think it's a problem, but it's easy to measure. Creep, again, I don't think it's a problem, and I'll show you why. And then you have durability and installation damage that I won't talk about, but they're well known. The ASTM has done an enormous service for us the last 25 years of developing test methods, standard ASTM test methods for these properties where you need them for the tensile strength and modulus, the seam strength, tensile tension creep, and friction, and so on, hydraulic properties, constructability, and so on. So now you can specify real ASTM tests for those properties. You don't have to go by what's in a manufacturer's brochure. So let me tell you a little bit about some of the research that was done by Stan Boyle at University of Washington. This was sponsored by Washington State DOT. Tony Allen was our contract monitor. He did in isolation and in load elongation tests on 2 different sands and then also strain gauges on the geosynthetic. This was prompted by the Rainier Avenue Wall, which is built just east of downtown Seattle. There's one of the tall buildings, reconstruction of I-90 about 25 years ago. And this was a temporary surcharge fill for some soft, or fairly soft lacustrine deposits that they were concerned about settling. And so this was done. Unfortunately, our structural colleagues in the bridge department weren't willing to let it be the permanent abutment, which it would have performed beautifully, but that's a whole other story. The wall was well instrumented, and the wall performed very well. I won't have time to go into all the details, but it was surcharged with a fairly high surcharge. It was 12.6 meters with almost a 6-meter high surcharge. The strains that were measured were all, you can't read this, but I'll tell you, they were all less, with one exception, extensometers and strain gauges, all less than 1%. This is a material that will fail at about 12 or 15%. So we're hardly using the strength of that material. So this led to some research that we did, and Stan Boyle built this device. It's a plain strain device with a geosynthetic that's shown schematically there, where there were airbags top and bottom. And so basically you're taking an element out of a reinforced soil wall and loading it just as you would with subsequent soil layers. And the idea was this would not go to failure. It's just to measure the in-soil modulus. One thing Stan found, when he first showed me this, I said, wow, that's really high. Look at the friction angle, 60 degrees, 62, 63 degrees. This is plain strain at very low confining pressures. So phi in plain strain is much, much higher. You start looking in the literature, and a lot of people have found this. Modulus, I won't take time to do it, but I'm going to show you something on creep. This was an incremental load test, and yeah, they didn't match the right and the left clamps, but this was the Rainier Avenue sand, which was an angular sand. The polypropylene 2 was the second layer, was a polypropylene woven, and 20 kPa was a confining pressure. So he takes it up to a little over 4% and lets it sit instead of going up until he reached the maximum that the machine was able to apply. And notice what happens. The load falls off. It relaxes. It moves. It's strained, but it relaxes. And then it sits there. And that's what happens in the real world. At working stresses, reinforced soil moves, relaxes, unless you come along and put additional load on, which might happen. So, bottom line of Stan's work, geosynthetics are much more efficient than steel because the strengths are both used more or less equally. With steel reinforcing, the steel does most of the work, and the soil kind of goes along for the ride. So if you want to use both materials, approximately the same, use a geosynthetic. Creep is not a problem, and I'm emphasizing this at working stresses. When loading stops, it'll deform as it relaxes. But it's in equilibrium, and it no longer moves unless it's loaded again. And this has been shown by field measurements of at least 2 walls, the one in Seattle, the Rainier Avenue wall, and John Fannin did some measurements on a geogrid reinforced steep slope. I think it was a 60-degree slope in Norway at 2 different types, 2 different densities, I guess you could say, of reinforcing. And he actually had a paper here in the 2013, I think, that showed, so he has almost 20 years of measurements. And boy, same thing, hardly moved, hardly moved. If you still think it's a problem, see Professor Bob Kerner and Grace Swan at Drexel. Scott Thornton, I had him in there, and I was just thinking about that this morning. Scott unfortunately passed away a few months ago. He developed this using isochronous load strain curves, or what he calls the step isothermal method, which is an ASTM standard. Tells you how to do it. If you want an elegant method, go to the British standards. The BS 8006, it has the unfortunate initial BS, but it's still the British standard. And John Fannin has gone through that. Basically what you're doing is taking 10,000 hour creep data and extrapolating out 2 orders of magnitude to, I think it's 114 years. It was pretty close to 120 years. And he has shown that you'll get the same answer as AASHTO with a creep reduction factor of whatever it is for the polymer. So if you really think it's a problem, you can, and you want to impress a client, go through this procedure. It is really very elegant. But probably just use that creep reduction factor that AASHTO recommends. But I don't think you need to. I think you can use 1 for that. Fine-grained soils, a lot of pressure, especially on private work, to use on-site materials. I can tell you 2 or 3 stories of that, of massive failures because of that. Avoid those if at all possible. Well, there still are a few things that we need to know and do. I'll tell you the 2 technical things are pretty simple. We need a poor man's plane strain device, something that will allow us to put in a triaxial cell and get a plane strain friction angle. Something simple. It'd be nice if you could measure volume changes so you can do plaxis and flak and stuff. And we need a seismic analysis procedure better than Mononobe Okabe. When was Mononobe Okabe developed? 1926? That's even before I was born. I mean, that's crazy that that's what we use. It's a pseudostatic thing. So I talked to Mike, I don't do dynamics, I leave that to Steve Kramer, my colleague. And I said, what should we use? And he said, well, the best thing I think is performance-based earthquake engineering. I said, well, where is it? Well, we're working on it. So anyway, they're working on it. But I can tell you, if you want to make, I won't promise you get rich, but if you're a student and you can come up with a plane strain device that an average consultant can use, it's no more complicated than a triaxial test. You won't get rich, but you'll get famous. And then come up with a performance-based earthquake engineering method that we can use to confirm that these structures are safer. I believe they are. They're very safe. I've got a lot of data that can illustrate that, but I think that's the thing. Now, the professional issues are a real worry. There are too many failures. It's been estimated there's something like 1 or 1.5% of these structures have had problems. That is a horrible record. And it's due to, it seems to be poor quality backfill, poor drainage, construction problems, the grid's going in the wrong direction, inadequate global or overall stability, and I showed you external stability, and I showed you some examples of that, unexpected surcharges, et cetera, et cetera. There is a disconnect between the wall designer, the geotecher record, and the site civil. And I can tell you again, many, many stories of that. That is silly. These folks working for different people, and they don't talk to each other. And mistakes are made on sites that lead to problems with these structures. And it's complicated by wall designs that are supplied by materials suppliers and distributors. This is really a bad situation. Now, my friends and myself, we make a lot of money getting involved with attorneys on investigating these things, but it doesn't have to be. There are other problems, lack of proper inspection. What? You mean you're putting up a huge structure and you don't have an inspector? Well, he's over there doing something, or we got a freeze on hiring, or we don't have money for it. No control of the construction by the designer. Economic pressures. If we can't get some engineers, if those engineers won't approve on-site materials, we'll get some who will. That was a job that failed in Prescott, Arizona recently, probably 10 years ago now. 60-some-odd foot high structure. Big box company, I won't say who, but that was their project manager. If we can't get those engineers to approve on-site soil, we'll get some who will. That's terrible. And I hope I don't, there are economic pressures to do that, obviously. And I hope I don't insult anyone, but I hate value engineering when it comes to this stuff. Now, I know it's all the rage and everything, and it may be good for foundations and other things, but it's terrible in this situation. Contractor supplied designs. Oh, have we got a deal for you, Mr. Owner? We can save you a lot of money. You know those geotechs are always over-conservative anyway. Everything's over-designed. And so then they come back to you and say, well, we want to do this. It's going to save some money. And then, so what happens? You say, well, gee, could I have some hours to check this? Oh, no, sorry, we've shot the budget for design, so too bad. What? We don't train workers. I've been on construction a lot, and I think workers would like to do a good job, but they don't know any better. So we need to take time to train the workers how you want the grids put in, what direction, some things like that. It's real simple to do, but somebody has to do it. And I've heard this in Seattle. I don't know if it's true here. Do you avoid liability by having somebody else do your design, vendor-supplied designs? I've heard that. Oh, we can't afford the liability. What happens if there's a problem? Yeah, they go right back to you, right? They aren't going to the guy that sold you the wall. He's a P.O. box in Atlanta or something, you know. What are they going to do? That's crazy. And if not, why do you give away good billable hours? I do not understand that. If you don't shift the liability to someone else, why do you give away those hours? And I can tell you, fixing problems is a lot more expensive than doing it right in the first place. Proper design and inspection controlled by the designer will save a lot of problems. I've heard numbers like a factor of 9 in 10 to fix structures that fail. And certainly if you calculate all the legal costs that go into repairs of failures and whatever else is involved, it's terrible. So anyway, that's I think a real problem. And I hope this is not true in the Northeast. But I can tell you in our area, there are jurisdictions, namely the city of Seattle and some of its suburbs, that say, aha, that's a wall. It's got to be stamped by a licensed structural engineer in the state of Washington. What do you mean? Structural engineers, you know, they're great people. They know a lot about reinforced concrete and steel. They don't know very much, in fact, probably nothing about geosynthetics and soil reinforcing. And whatever they had in their undergraduate soil mechanics and hydraulics know a little bit about drainage and soils. And then besides, they're not responsible for the inspection. What? And yet, I can tell you stories of failures there. And I thought that was just our problem. And I gave some lectures in Australia recently. Well, it was a couple of years ago now. And a guy came up to me afterwards. They had their little happy hour afterwards and not before. And he said, oh, while I was waiting for you to get started, I found this brochure. And I'm sorry I didn't bring it in. I was thinking about that this morning. I should have brought it to you. It was from the Institute. The talk was in Sydney at the Institution of Engineers of Australia. Ooh, boy, that sounds pretty good. And there was a brochure there that said, need a retaining wall? Hire a structural engineer. They got the same problem in Australia that we do. You have a retaining wall? Hire a structural engineer. So I don't know how to fix this. This is leading to all those failures I mentioned earlier. They're costly, potentially tragic. I gave this talk up in Ontario, and Richard Bathurst said, oh yeah, there was a wall that failed in Panama and killed some children. And the designer and supplier came in with big rolls of Franklin's and bought off the family. Can you imagine what would happen to this technology if that had happened here? Hits the papers, kids killed in South Carolina from a collapse of a reinforced wall. That would kill this technology. Now, there are some, I don't know who is responsible for that. I don't know how to fix it. Is it the Geo Institute, the ASFE or whatever it's called now, Geotechnical Engineering Association or whatever it's called, Business Association, International Geosynthetic Society, ISSMGE. Is it up to us as individuals? They're not, a lot of these issues about hours for the designer and proper inspection is not unique to geosynthetic reinforced soil, but it threatens this technology. It's a wonderful technology, and I think it's a threat to our profession. And I wished I had an answer for you on that. But like I said, I want to end on a sour note, so I want to end on successful. And this is in Colorado, a bridge abutment on shallow foundations crossing an interstate highway, I-25, near Denver. And it was very heavily instrumented as geogrid reinforced modular block face wall, performed beautifully. Enormous amount of money saved on piles that they had to pre-bore through those stiff clays to get the piles in. But that was their standard practice. All bridges have to be on piles. In Colorado, Bob Barrett, that guy I showed you earlier, has done a lot of work with different faces, timber, modular block, or cement blocks as he calls them, natural rock, colored cement in the concrete. I think some wonderful things. And then you find some walls, probably a lot of these are steel reinforcing, but you find some wonderful things to make them less ugly. Walls are ugly. And so if you can make them less ugly, that's pretty good. The modular blocks that have been developed, these precast concrete blocks, and you can go around corners and you can do a lot of stuff that really are quite attractive. And green facings, I told you about this. This is with a steel wall, but it's developed that. It was totally unplanned in a wet climate. Same thing in Taiwan. You can see the grids are still stacked here. They haven't even finished construction. And already in a subtropical climate, natural vegetation is established. And I'm sure it was for a housing development. You go up here and up, they were going to build houses up here. I'm sure in a few years you won't know that that was a reinforced soil slope. All these people driving up there and live in their houses, they never know that they were working on reinforced soil. And here you can see the facing system. I had a chance to go down to Colombia a few years ago, and compliments of Geosistemas Pavco, which is a manufacturer. And they took me out and showed me some of these structures. This is the way they do rural highways with sandbags, bring backfill in and the geosynthetics and then build them up very, very fast. And it works beautifully. They've done some really nice jobs. These two photographs I took in Medellin, up in quite a ritzy part of the city, gated community and all this sort of thing, and some really expensive homes. And that's all reinforced slopes. And then I got these photographs from this guy, Fernando Cano of Medellin, and he said, you can use these to show your friends in North America, but please tell everyone that not everyone in Colombia, please tell your friends in North America, he said, that not everyone in Colombia is a drug trafficker or a guerrilla. And I'm happy to say that these engineers in Colombia, and I've talked to landfill folks as well as reinforced, they are very innovative. They've done things that I think put us to shame. And we think we're, the best in the world and all that sort of thing. But I got to say, the folks in Colombia are fantastic geotechnical engineers. And some slopes, Northern California and Northern Idaho, reinforced soil. And then I almost took this out this morning because this has failed. And nobody knows why yet. We were talking about this before. They hadn't quite finished when this photograph was taken. It was taken out of an airplane window. You can see a drop of rain. The guy that took it gave it to me. They still had 20 or 30 feet. You can see the construction equipment here. This is a big slope, 250, 260 feet, something like that. And it failed, just recently. You can go in and look at Yeager Airport, Charleston, West Virginia, and there's some wonderful photographs. There's some TV footage. It is spectacular. I'd love to be able to tell you what happened, but that has happened. Earthquakes, very forgiving. This is the Japanese National Railway in Kobe. Kobe was devastated, as you can see here, 1995 and 92. It's not exactly the same place, but the same stretch of the wall that it settled and moved, and it went for a ride looking at that damage. And the JNR was still operating the next day. So they're very forgiving, very flexible. So finally, what I've tried to do is to show you that geosynthetic reinforced slopes and walls have started with experimental, small-scale, low-risk projects that certainly weren't readily accepted back in the 70s and 80s to, I think, almost routine today. I'll make a prediction. It's easy to make predictions, especially when you get older, because no one's going to check you. Geosynthetic reinforced soil will soon be the standard steep slope and standard wall of the future. I think there are so many advantages, and I've shown you some examples. There are a few technical and professional issues that remain. I don't know the answer to those, and I invite you to try to do something about that if you can. Prediction for the academics, GRS and other types of walls. And I think it'll change the way we teach retaining structures. I think eventually it'll come to that. So I acknowledge my former professors and colleagues, former Tatsagi lecturers that I had the pleasure of working with at different times who taught me geotech and geosynthetics, and certainly my former students. Pedro Arduino and Steve Kramer, my two University of Washington colleagues, are still trying to teach me modern soil mechanics. You know, it's kind of hard to teach an old dog new tricks. And the GI board that had selected me for this, and my wife for her support over the years. And I thank you for your kind attention. Sorry, I think it was.
So we have time for some questions. Don't be shy. Wow. There's one.
Okay.
He's a structural engineer, so be careful.
Okay. Well, good. Yeah.
Okay.
One of your slides indicated the rate of construction was an important factor. Can you elaborate on that?
Well, this came out in trying to model, how do you model it? If you're going to model it the right way, you've got to have the rate of construction and take that into account. And especially this was true with the poor quality backfill and the foundation that would settle during the time. So if you're going to do, this was flak that my student used, she found that she had to model the compression of individual layers as she went up, otherwise she couldn't get the right answer. So that's basically it. Yeah. But watch these reinforced soil things. I mean, you design your reinforced concrete cantilevers and your bin walls and some of those to your heart's content. But well, I got to tell you, if you get involved with geosynthetics, you need to know what you're doing. And it's not hard. I think anybody can design a regular retaining wall can design a geosynthetic reinforced wall. So just a few extra steps. It's not that hard to do. So I encourage you to learn how to do that because it's easy to do. Yes?
He's another structural guy.
Oh, okay,
Another
sorry.
structures guy.
Hope I haven't
Is this
insulted
on?
you.
Yeah.
They're very upset.
Yeah. No, I hope not.
No, I have a question. You mentioned that 1%, 1.5% of these reinforced walls failed and we should do a better job. Then you mentioned performance-based. You mentioned performance-based earthquake engineering, but
Yeah.
I guess performance-based design will come into play here. Is there anybody working on a design procedure that targets failure probability or a reliability level for these systems?
Some people
And
have-
what is the state of that work?
There have been people that have done risk assessment kinds of things, and I think they've shown what Barry Christopher and Jonathan Cheng showed years ago, that these systems are a lot more reliable, for everything else being equal, than unreinforced systems. So you can do all sorts of risk analyses and probabilistic design and so on, and I think that's what it'll show. I don't know if that's come into practice yet, just like other things. We're not very good at that. That's probably the way we ought to design everything, slopes and foundations, but we don't. I don't know if that answers your question, but...
There's another structural engineer there.
Oh. Yeah, well, good. Yes, sure, Majid.
If you compare the long-term performance and short-term performance, so based on the relaxation behavior, you would expect the long-term performance to be better, right? If there is no compression depth.
Yes, and I think that's the answer, that the measurements that we've made long-term, we haven't been very many. The Rainier Avenue wall was a temporary wall, and so it was torn down after about 9 months. But John Fannon's reinforced steep slope in Norway, that was built in 1988, I think, or 87. So he's got almost 20 years of measurements. And yeah, the measurements, after a while, the strain gauges stopped working and that sort of thing. And the guy that did the measurements for the Norwegian Geotechnical Institute retired, and you can tell that whoever came in afterwards was not as careful, and they went through some winters and so on, but it suggests that there's not a lot of change in those. And I'm surprised no one's asked me about durability of these materials, but Well, they don't rot. Plastics don't rot. And you're in a benign environment, you know, pH of 7, and doesn't have a lot of oxygen in there. They're not going to oxidize. They're not going to degrade in typical backfills. In fact, the Federal Highway spent a lot of our money doing polymer longevity studies and all this sort of thing, and they found that the half-life of typical reinforcing geosynthetics is between 500 and 5,000 years. That's the half-life. What's the factor of safety of these materials? Sure, we calculate 1.5 or 2. It's probably closer to 8 or 10 real. The Federal Highway, for example, in ASHO, they say assume 34 degrees. It's hard to find any natural soils that are 34 degrees that are free draining. I mean, just any kind of compaction, you got 34, 35, 36 degrees, even with, well, not quite marbles, but you know, Ottawa sand will do that. So come on, right away, and then you add the plane strain, huge factors of safety there. Yes?
Can you comment on the deformation criteria that ASHO gives?
It's conservative. If you're talking about that L over H and that, yeah, it's that was developed based on finite elements and back analysis of some full-scale work that was done by Barry Christopher. That was part of his PhD thesis. And Stan Boyle did some studies on reinforced systems looking at deformations where you have a few measurements, short-term measurements. And he found that everything was kind of above that curve, so that curve is conservative. That's fine. That's good. I told Barry that, and he said, good, I like to be conservative. So it's not bad. But you've got abilities nowadays to do some pretty good modeling if you have the right input values. If you're really concerned on a critical structure, you can do FLAC or Plaxis, and if you got the right input properties, and get a pretty good handle on that. Well, if you have anything else, any more? Anything else?
These students, these undergrads, they don't know, but they're going to get 10 questions on the final on your talk.
Oh boy. Woo. Well, good luck.
Just,
okay, sure.
Bob, maybe you're aware, the LRFD method is a probability of failure method that's been
Yeah,
embraced
it's supposed to be.
by
Yeah.
you know, FH,
Yeah.
and Transportation Research Board, you know, gives classes on it, and
Yeah.
of course it takes in probability of failure into the design based on the ramifications of the failure
Yeah.
as well. So,
Which I'm
just
sure
to address your question.
anybody that does these kinds of designs thinks about what can possibly happen to this structure. And you know, any good designer would do that anyway, even if you don't have this formal procedure. And the problem with LRFD for these types of structures, I know there are books and manuals on this, but no one has ever told me if I use that procedure versus the old traditional method that I'll come up with a more economical or safer design. Yeah, because they back-figured all the coefficients to get a factor of safety of 1.5 or 2. At least for this technology. I don't know if that's true for piles or other things, but so I know that there's a real push to do that, but I'd like to be convinced that I would get a safer and better design than I wouldn't otherwise. If somebody can convince me, I notice they've taken away the wine, so you'll have to work hard at convincing me.
I was going to buy everybody a drink, but it's
Oh,
closed.
gee, I should buy everybody a drink.
So,
Okay.
well, thank you again.
Oh, you're
Bob.
very welcome.
Really appreciate it.
Oh, thank you. Thank you.